Alessandro, please.
Thank you. Thank you. So our next speaker is Pablo Suarez Serrato. He's a professor at the National Autonomous University of Mexico, and he will present examples of symbolic and computational and numerical computation in Poisson geometry. So I guess we can now see the video, and just to remind that if you have questions for the online participants, you may ask them in the chat, and then I will read them for Pablo. So please, let's start the video.
In this video, we explain how to use Poisson geometry and numerical Poisson geometry, two Python models for symbolic and numerical computation in Poisson geometry. For this, we will use Google Colab, a free cloud-based online Jupyter Notebook environment that allows you to write and run Python code in real time. Installation. First, to install the latest stable versions of our models, we run this code line to install Poisson geometry and this code line to install numerical Poisson geometry. Then, we must import the classes of our models, Poisson geometry and non-Poisson geometry in that order. And we can do this with an alias for simplicity. For example, with this code line, we import the class Poisson geometry with the alias PG, and with this code line, we import the class num Poisson geometry with the alias NPG. Finally, it is necessary to instantiate the classes PG and NPG by entering the dimension in which we want to work. For example, to work in dimension 6, we enter this number as an argument of PG and NPG. With this instance, the symbolic variable that names the coordinates is X by default. In addition, we assign each instance to the variables PG6 and NPG6 for simplicity. Syntax. The methods in our models take scalar function, multivector fields, and differential forms as inputs. The syntax of Poisson geometry and numerical Poisson geometry are the same. Scalar function. A scalar function is written using string-type expressions. For example, this function should be written as the following string expression. Here, x1, x2, and x3 are symbolic variables that are models defined by default, and that here represent the coordinates x1, x2, and x3 in that order. A character that is not a symbolic coordinate is treated as a symbolic parameter, like A, B, and C in this example. We recall that Python supports the following basic operations: addition, subtraction, division, multiplication, and exponentiation. Multivector fields. A multivector field is written using Python dictionaries where all the keys are tuples of integers and all the values are string-type expressions. For example, this vector field should be written as this dictionary. Here, each key corresponds to the index of the basic vector field. This key for the partial with respect to x1, this key for the partial with respect to x2, and this key for the partial with respect to x3. The corresponding values encode the correspective coefficients. Here, we remark that we can change the order of the keys and of the corresponding value. For example, if we reverse the order, this dictionary encodes the same vector field above. Now, this bivector field may be written as this dictionary. Each key corresponds to the indices of the basic bivector fields. This key for this bivector field, this key for this basic bivector field and this one for this bivector field. The corresponding values encodes the respective coefficient x3 minus x2, x1 in this example. Here, we recall that the order of the indices in each tuple can be changed according to the skew symmetry of the exterior algebra operators. For example, this dictionary encodes this bivector field. If we permute the basic vector field with respect to the wedge operator, we get a minus sign. Then, to encode this bivector field as a dictionary, we must permute the integers of this tuple in the same way and add the minus sign in the corresponding string. Yes. Differential forms. The syntax for differential forms is the same as for multivector field. For example, as before, this differential tool form must be written as this dictionary. As before, here each key corresponds to the indices of the basic differential tool form. This key for the differential of x1, wedge differential x2, and this key for the differential of x5, wedge differential of x6. The corresponding values encodes their respective coefficients. Meshes for numerical evaluations. In numerical Poisson geometry, it is necessary to define meshes to evaluate objects. We must enter a mesh as list of lists. For example, in dimension 6, this array encodes a mesh with these 3 points. In particular, we can use NumPy arrays. If we import NumPy as NP, to create a 1 billion by 6 NumPy array with random samples from a uniform distribution over 0, 1, we use the random run function of NumPy. Examples of our symbolic and numerical methods. Now, we present an overview of examples serving as simple illustrations of how our two models can be used. First, we show how to work with Poisson brackets. If we consider the bivector field on R6 pi given by this formula, we can verify that pi is a Poisson bivector field with the function is Poisson bivector of Poisson geometry. To do this, we encode the bivector field pi in a Python dictionary, which we store in a variable called p. Then, using the instance pg6, we execute the function is Poisson bivector with parameter p, and we get the return true. Since the output is true, pi is a Poisson bivector field. Moreover, we can verify that pi is not a symplectic Poisson bivector field. First, we compute the matrix of pi using the function bivector to matrix of Poisson geometry. Next, the function det of sim pi returns the determinant of this matrix. Since the output is 0, this matrix is not invertible, and hence pi is not symplectic. However, we can compute the Poisson bracket induced by pi of two scalar functions, for example, f and g, given by these formulas. First, we encode f and g as a string expression of Python, which we store in variables called f and g. Then, if we run the function Poisson bracket with parameter p, f, and g, we get the Poisson bracket of f and g. From this formula, we can easily conclude that the Poisson bracket of f and g with respect to pi is 0 at points of R6, such as that x4, x5, and x6 are equal. We can check this fact with the function num Poisson bracket of numerical Poisson geometry using a random mesh of this shape. Here, R is a fixed real number, and the samples A, I, B, I are uniformly randomly selected from 0, 1. We can generate a mesh of this type by using the function uniform and run of numpy, which we store such a mesh in a variable called mesh. Finally, if we're running the function num Poisson bracket with parameter p, f, and g, we have that the evaluation of the Poisson bracket of f and g with respect to pi on this mesh is 0. Observe that in this example, the output is a PyTorch tensor because of this flag. Now we show how to compute and numerically evaluate Hamiltonian vector fields. Consider the symplectic or canonical Poisson vector field on R6 pi and the function h given by this formula on R6 minus this line. We can compute the Hamiltonian vector field xh of h with respect to pi as follows. First, we encode pi as a Python dictionary, which we store in a variable called p, and we encode h as a string expression of Python, which we encode a variable called h. The function, the method Hamiltonian BF with parameter p and h returns the Hamiltonian vector field xh encoded as a Python dictionary. From here, we have that the xh is given by this formula. To evaluate xh on a mesh in R6, we can use the method num Hamiltonian BF of numerical Poisson geometry. For evaluation, we use the mesh defined in a previous cell. Finally, the method num Hamiltonian BF with parameter p, h, and mesh return the evaluation of the Hamiltonian vector field xh on this mesh. Observe that we only need the algebraic expression for pi and h to carry out the numerical evaluation and not the Hamiltonian vector field xh explicitly. In this case, in this example, the output is a TensorFlow tensor because of this flag. Moreover, we can use our symbolic model to compute the Hamiltonian vector field of an arbitrary function. For example, consider the non-symplectic Poisson vector field on R6 pi s parameterized by a scalar s and given by this formula. Since we are working with the variables y on R6, we need to instantiate Poisson geometry to work in dimension 6 and with the symbolic variable y with this flag. So first we encode as before pi s as a Python dictionary, which we are stored in a variable called ps. The method course of Poisson geometry returns the symbolic variables in which we are working. In this case, y1 to y6. With this, we can define an arbitrary symbolic function using the method function on sympy. We store this symbolic function in a variable called h. This symbolic function depends of the variables y1 to y6. Finally, with the function Hamiltonian BF and with parameter PS and H as a fs string of Python, we can compute the Hamiltonian vector field of this symbolic function H. This output says that the Hamiltonian vector field of H with respect to pi s is given by this formula. Modular vector fields. In this part, with two examples, we will see how our models help to determine the unimodularity of homogeneous Poisson by vector fields. Since our first example is on R4, we instantiate Poisson geometry to work in dimension 4. Consider the Poisson by vector field pi1 on R4 given by this formula. The method modular BF of Poisson geometry computes, in general, the modular vector field of a Poisson by vector field on Rm with respect to the volume form f omega 0, where f is a non-vanishing function and omega 0 is the Euclidean volume form on Rm. So in this case, to compute the modular vector field C of pi1 with respect to omega 0, we first encode pi1 as a Python dictionary, which we store in a variable called p1. The modular BF with parameter p1 and string 1 return the modular vector field of pi1 with respect to the Euclidean volume form. Since their output is an empty dictionary, we conclude that C is 0, and hence pi1 is unimodular on all of R4. Example 2. Consider the following homogeneous Poisson by vector field pi2 on R3, given by this formula. Since this example is on R3, we instantiate num Poisson geometry to work in dimension 3. To evaluate pi2 on a mesh in R3, first we encode pi2 as a Python dictionary, which we store in a variable called p2. To generate a mesh on R3, we generate a 1 billion by 3 numpy array with random samples from a uniform distribution over 0, 1, using the function run on numpy. The method num modular vector field with parameters p2, string 1, and mesh returns the evaluation of the modular vector field of pi1 with respect to the Euclidean volume form on this mesh. Since there are points for which the modular vector field of pi2 with respect to the Euclidean volume form is not 0, we conclude that p2 is not unimodular on R3. This is important. Observe that we use a probabilistic method to verify a particular property of a Poisson by vector field. These methods can be used to determine other characteristics.
Thank you, Jose Ruiz. Maybe I should apologize because in the end it was Jose Ruiz, the one presenting. So thank you, Pablo, for telling me that. And we have the possibility for just one question, I've just been told. So there is a question in the chat, and it's by Marcello Seri. He is asking is it possible to support exponentials and trigonometric functions? So Pablo or Jose, any one of you, if you want to answer the question.
Yes, it is possible. I mean, any sort of function that can be written in SymPy, you can use it. I guess the real limitation is writing a function that is actually computable. So that's something that maybe should be stated, but obviously because these are functions that have to be fed into a computer, they need to be computable. So if you have some very, very complicated expression in terms of an integral that might not be computable, then that would be problematic, but that's just the nature of computing theory as such. But in principle, anything that you can write down in SymPy should go through. And yes, the presenter was Jose Ruiz. This is also joint work with my PhD student, Miguel Evangelista. And well, thank you very much to everyone. And it's a pity we couldn't meet in person, but I hope to be in touch at some other point in time.
Thank you. Thank you, Pablo. I guess Marcelo is satisfied with the answer he wrote in the chat. So thank you, Pablo and Jose again for this nice tutorial. And we'll move to our next speaker, who is Marcello Seri. He is a professor at the University of Groningen, and he is going to present new directions for contact integrators. So please, let's run the video of his presentation.